Thanks, Raghu, and thanks to the organizer of this workshop for inviting me. So as Raghu said, I'm going to be talking about Boolean circuits, Boolean computation, which is a slight change of context from what we've seen so far in this workshop. But hopefully I'll set up enough notation that it will not be very discomforting. And plus, we'll see some of our friends like polynomials, etc. So you should not feel like it's completely unrelated to things we've seen so far. Okay, so what is Boolean function complexity about? So what is a Boolean function? Where our Boolean functions are just functions that take bits to a bit, right? So you have n input bits, and you output some sort of bit, and that's your computational problem. Okay, so you want to compute a function of this form. And we're going to be looking at Boolean computational models. So our algorithms will be kind of expressions for f, for this Boolean function, and these expressions are constructed using pre-agreed upon simple operations of some form. Okay, so just to get concrete, so simple operations are things that we all know and love. So for example, the AND function, right? You have the AND of some m input bits. You have input bits x1 through xm, and you output 1 if all of them are 1 and 0 otherwise. That's a pre-agreed upon simple operation. You might have the OR function or the NOT function. So these are all things that we understand, and I hope you'll agree with me that they are simple enough that we can use them as atomic elements in our expressions. Okay, so using these expressions, we can construct more complicated ones by composing them successively with each other. So for example, I could have a function of 5 bits, which I write as an expression involving NOTs, ANDs, and ORs in this way. Okay, and this for us is a computational model, right? So a small expression is kind of an efficient algorithm, a large expression is an inefficient algorithm, but this is how the algorithm works. Okay, so what does this particular algorithm tell you to do? It tells you that if you want to compute f, so such a thing is called a Boolean formula, by the way, analogous to arithmetic formulas, which we've seen already. And so what does this algorithm tell us to do? It says if you want to compute f on inputs x1 through x5, you take x1 and x2 and you take their AND, that's this guy here, and then you take NOT of that, similarly, and then take the OR of that with x3 and the AND of x4 and x5. Okay, so this tells you a way to compute the function using these simple operations and your input bits. Okay, so every such expression gives rise to an algorithm. And of course, whenever we have an algorithm, we'd like notions of efficiency to associate with it. So we'd like to know, is this a good algorithm? Is this a bad algorithm? So what's the notion of efficiency? So a natural notion of efficiency when it comes to Boolean formulas, well, there are two notions of efficiency. There's the size, which is the number of operations you use, right? So if there's a really big expression, then it's not a very efficient algorithm. It tells you to do lots of stuff to compute the Boolean function. But if it's a small expression, then it's an efficient algorithm. So the size, which is the number of operations you see in this expression, that's a notion of efficiency. Another notion of efficiency is the depth. Okay, so how, as a graph, how tall is this graph? So what's the longest input node to output node path in this graph? Okay, that's the depth of the algorithm. So that kind of measures how parallelizable this algorithm is. Okay, all right. So we're going to look at both of them, but for us, usually the depth will be a constant. So you should think of the depth as like 100 for the rest of the talk, and the size is something that's growing with the number of variables, and that's what you're looking at. Okay, so this is a kind of a pictorial representation of the same expression above, so there's no difference. But the nice thing about this expression is that it suggests generalizations. Okay, so what is this expression? What does this look like? This figure is that of some sort of directed tree, right? And this tree tells you how to evaluate the variables in order to compute your function. But you don't necessarily have to have trees. You could also have DAGs. Okay, right? So you don't. So in the previous diagram, you don't really have any cycles here. But you could have cycles as long as they're not directed cycles, and that's also a reasonable way of computing your Boolean function. And these DAGs are called Boolean circuits. Okay? So Boolean circuits is just Boolean formulas, only you can have these cycles which are not directed. So for example, the variable x2 here participates in some sort of cycle. All right? And again, here you have notions of efficiency. You have depth, which is well defined, and size, which is again the number of operations. All right? So two ways to represent Boolean functions: Boolean formulas, just an expression or a tree. Boolean circuit, which is a DAG like this. So now you can ask, is one more expressive than the other? Are Boolean circuits, can they represent functions that Boolean formulas cannot? Well, it's easy to see that's not the case, right? So for example, if I have a Boolean circuit, this particular Boolean circuit, and I want to make it a formula, well, why is it not a formula? Because this x2 guy is participating in a cycle. What I could do is make 2 copies of x2 and come up with a formula like this, right? So I could always do that. And now I've changed my Boolean function, my Boolean circuit to a Boolean formula. And I'm still obviously computing the same function. Yeah, and I could always do this. I can always convert a circuit into a formula. But the resulting formula that I constructed is slightly bigger. So for example, here I started off with 6 nodes. and the size is, after this blow up procedure, this replication of x2, the size becomes 7. Okay, so a slight increase. All right. And this can be done in general, right? So this is just an example, but it can be done in general. So suppose I have a circuit of depth 3, is it 3? Yeah, depth 3 here, right? And I have all possible interconnections, right? This is the thing about circuits. You can have all sorts of cycles. So you can have all the guys here, use all the guys here, all the guys here, use all the guys here, and so on, right? I could convert this into a formula in exactly the same way. So for example, I would replicate all these guys here 3 times, once for each of the nodes here that use them, right? And then I would replicate these guys for each of the nodes that use here that use them. So I would replicate each of these guys 9 times. And this kind of replication blowing up procedure in general converts a circuit into a formula. But in this case, you can see that the amount of replication increases with the depth, right? So the more the depth, the more you have to replicate, the larger the blow up. Okay, so in this case, you end up with 27 vertices on the bottom layer. Okay, so in general, if you have a circuit of size s, right, s operations, size s and depth d, the formula you construct by this trivial blowing up procedure has size s to the d, so there's an exponential dependence on depth, but it also has depth d. Okay, so you don't increase the depth, but you blow up the size, right? And the question that motivates this result is this optimal? Right? So can you improve on this trivial circuit to formula conversion? Okay, all right. So that's the question: can every circuit of size s be converted to a formula of size? Do you need this blow up of s to the d, or can you do something better? Okay, so notice that I'm not here restricting the procedure in any way. So what I'm asking now is, can you come up with some formula, any formula in your favorite way, in a completely different way, that computes the same function as the circuit, but now has size much smaller than the trivial blow up that we just incurred? Okay, the question clear to everybody? Right. So in this question, there's no restriction on the depth, but the questions I'll be looking at, the depth will be restricted. So the expected answer to this question is no in many regimes. So for example, if you don't expect that undirected ST connectivity, kind of a very reasonable problem on graphs, has smaller formulas than we know currently, if you don't expect that, then the answer to this question is no. So there are many regimes in which you expect the answer to be no, but we don't know how to prove that yet. Okay, so in this particular result and in some previous results, we look at the case of constant depth. So we restrict the depth to a constant. So think of depth equals 100, as I said. And now we try to ask, okay, is it true when the depth is a constant? So the circuit depth is a constant, and we want a formula of the same depth that computes the same function as the circuit. Okay, can we do any better? All right. Okay, so that's the question. Is this clear to everybody? Okay, yeah, I should say, yeah, feel free to stop me at any time and ask questions. Okay. All right, so that's the basic question. So let me first now do a little bit of a digression and set up some notation related to constant depth circuits, and I'll come back to the question that I just talked about. Okay, so one very famous class of constant depth circuits where this question has been studied is a class of AC0 circuits. So what are AC0 circuits? They're circuits that are made up of our simple operations, right, and, or, and not. So they're made up of these simple operations, but they have constant depth. Okay, so for example, D equals 2, this is something that you call DNF or CNF formulas. So AC0 circuits of depth 2 are things that we understand very well, but you can also look at larger depths. All right. So here's some background work on AC0. So AC0 is actually a classical circuit class in the sense that it's been studied since the early 80s, at least, and we have a large body of work relating to AC0. So let me just give you a tiny survey on what's known. Okay. So here's a basic fact about AC0. It's complete. What does that mean? It can compute every possible function, right? So given any Boolean function on n bits, you can write, in fact, a depth 2 AC0 circuit computing it. So a DNF or a CNF formula that computes this function. But the formula, unfortunately, has size 2 to the n. So it's exponentially large. Okay, right? It's also known that this trivial construction, in some sense, cannot be improved because there are functions for which any AC0 circuit, in fact, any circuit, but in particular, any AC0 circuit computing these functions has size at least 2 to the n by 2. Okay, all right. So every function has a circuit of size 2 to the n, and that's kind of trivial. But unfortunately, this trivial bound cannot be improved for some functions. Okay? And the proof of the second thing is actually a very kind of simple counting type argument. You just count the number of circuits of size less than 2 to the n by 2. You count the number of Boolean functions on n bits, and you see that one is more than the other, so there must be Boolean functions that don't have small circuits. Okay? So it's a very trivial bound. So what we'd like to do is to make these bounds explicit. So we'd like explicit examples of simple to state functions that do not have small circuits. Okay? So that's a basic lower bound question for AC0. And it's not quite the question we are looking at in this talk, but it's closely related. So let me say something about it. So we do have such functions. We do have explicit functions that do not have small AC0 circuits. So what's an example of one? Well, the classical example is the parity function. Okay, so what's the parity function? You have n bits, and you're just summing them modulo 2, right? You output 1 if the number of ones is odd, and 0 if the number of ones is even. Okay, it's known that the parity function does not have small AC0 circuits. All right. Okay, so yeah, I'm not going to talk about the proof of this, of course, but there is a very intuitive reason to see why you might think of the parity function in this context, because it has this very nice property that's not easy to fix the value of the parity function, in the sense that if you're just fixing the inputs of the parity function to zeros or ones, right? I'm allowed to take x1, set it to 0 or 1, x2 set it to 0 or 1, etc. I'm allowed to do a few fixings of this form. It's very difficult to pin the parity function down to a certain value. In fact, unless I have fixed all the bits to fixed values, I cannot really fix the parity function down to a certain value, right? If I fixed n minus 1 bits, let's say to all zeros, the parity function still depends on the last bit remaining. Okay, so it's one of those functions that's very hard to pin down. And this is in contrast to the building blocks of the AC0 circuits, right? What are the building blocks of the AC0 circuits? Well, the AND and the OR. Okay, the NOT gate is kind of simple; it depends on only one input bit. But the AND and the OR are kind of the main building blocks, and they definitely do not have this property, right? Because I could have an AND of 100 bits, and if I fix one of them to 0, the remaining are irrelevant, so it gets fixed to 0. Similarly, if I have the OR of a large number of bits and I fix one of them to 1, the OR function becomes 1. So they are definitely not like the parity function. So you would think naturally that circuits constructed of mostly of AND and OR gates cannot compute something like the parity function very easily. Okay, and indeed this turns out to be the case. So there is a classical line of work starting from the very early 80s, Oitoy, first Sipser, etc., culminating in the result of Hostad in 86, I think, that says that any depth d circuit for the parity function, so right, so parity function on n bits, any depth d, think of d as 100, right? Any depth d circuit for the parity function has size at least 2 to the n to the 1 over d minus 1. Okay, that's 2 to the n to 1 over d minus 1. So I'm going to be a little pedantic with some parameters here, not all of them hopefully, but with some of them. So let me just write this down a little carefully. So suppose you take d equals 3 here, you get a lower bound of 2 to the square root n. I'll ignore the constant in the exponent. If you take d equals 4, you get 2 to the n to the 1/3, and so on. D equals 5, 2 to the n to the 1/4, etc. Okay, so this is the parity lower bound. All right. Yeah, absolutely. So this bound is tight. I'll just come to that. Yeah, that's very important, right? Right, so there's a constant in the exponent. I'm not writing it down here, but it's an absolute constant. So when I say depth equals constant, you might think I'm hiding something depending on the depth in that omega, but I'm not really not. It's just an absolute constant. So think of there being 1 over 10 here. So some reasonable constant. Okay, and that's unfortunately important, so you have to pay attention to that. Okay, all right. Okay, so that's Hostad's theorem. Any depth d circuit for parity has this much size. And the amazing thing about it, this is exactly what Surijit was asking, this is tight. Okay, this is tight up to the constant in the exponent. There are circuits of size 2 to the order n to the 1 over d minus 1 for every depth d. Okay, it's actually not very hard to construct. And in fact, here the constant in the order is 1, I think. It's just 2 to the n to the 1 over d minus 1. Okay. The idea behind this is very simple divide and conquer algorithm. You write the sum modulo 2 as the sum over, so you block it into blocks of some size, and you compute the parity inside each block with some brute force algorithm. Then you take parity of that again by blocking it, etc., etc. So you do a suitable divide and conquer, and you will get something like this. Okay. Any questions about this at all? The parity lower bound? Okay. Good. Right. So it's an amazing result because we have a strong lower bound, an exponential lower bound, and it's tight. You really cannot improve this. So it's almost completely tight. So people have also looked at the case of nailing down the constant in the exponent, and for the case d equals 3, that's known actually. So the constant is 1. All right.
So this upper bound gives a circuit and not a formula.
This upper bound gives a circuit and not a formula, and there's a very good reason why it doesn't give a formula. Okay. All right. So that's some general stuff about AC0. But now let's come back to a circuits versus formulas question. All right. And so Rossmann considered this question in the context of AC0 circuits versus formulas. And he proved that the trivial blow up when going from circuits to formulas where you exponentiate to the depth is kind of tight. And it's tight simply because of the parity function. Okay. So what he showed was that any formula of depth d, right, so it's not a circuit now, it's a formula of depth d for the parity function, has size at least whatever we got earlier, but there is an additional d in the exponent. Okay. So yeah. So d equals 3 doesn't make sense, but 2 to the whatever you get times a d, and then there's some universal constant that doesn't depend on d. Okay. And this is a really amazing reworking of Hofstad's proof with some very clever work to ensure that you use the fact that it's a formula and not a circuit you're fighting against. Okay. All right. Right. So and recall from the previous slide that we do know that the parity function has depth d circuits of size 2 to the n to the 1 over d minus 1. So putting this upper bound, which is at the bottom, and the lower bound, which is at the top, together, you see that for when d is a constant, this trivial circuit to formula conversion in the context of AC0 is tight. Right? So for this particular circuit, any formula that you construct, not necessarily by the blow up procedure that we described, but in any way, will have size 2 to the d times n to the 1 over d minus 1. So you will get the blow up. Okay. All right, great. So is this result? This is fine. Okay. All right. So onward from Rossmann's theorem. So what we'd like to do is push this result forward, right? What other circuit classes can we prove this for? What are stronger circuit classes ideally that we could prove this for? Well, the most natural thing to do at this point is to relax the depth equals constant condition. Okay. So he proves it for constant depth. Can we relax the condition? Well, actually, if you look at Rossmann's theorem, it doesn't just work for depth equals constant, it works for depth up to roughly log n, slightly smaller than log n, asymptotically smaller than log n. It works almost until there. So can you push it to log n? Okay. We would love to push it to log n, but we have no idea how to push things to log n. Okay. This is like a 20-year-old problem in circuit complexity. For circuits of depth log n, we don't know much, and in fact, we don't even know how to answer simpler questions. Forget about the circuit versus formula separation. Okay. So this is not a feasible problem as of now. So therefore, we are not able to handle this larger depth scenario. But what we are able to do is now allow for a richer set of operations. Okay? And this richer set of operations is obtained by adding to the circuits the power to compute the parity function. Okay? So what did we just show? We show that the parity operation is not something that can be done just with AND, OR, and NOT gates alone. So now you can look at the circuit class you get where the parity operation now comes for free. You have a parity gate. So now it's trivial to do the parity operation. So it's clear that this is a much stronger circuit class. And now you can ask whether the circuit to formula conversion for this class is optimal. Okay. Right. So it's so this is the class of circuits or formulas we consider, AC0 parity circuits, so parity formulas. So you have AND, OR, and NOT as before, but now you also have the parity operations. Now can you prove a similar result here? Okay. And that's the main result. So the same kind of result for AC0 with parity gates. Okay. Yeah. Actually, the result is a little bit stronger. So let me state it formally. So there is a Boolean function f on n bits. Unfortunately, it's not the parity function because we know the parity function is trivial for this class. There's a Boolean function f on n bits such that it actually has an AC0 circuit. It's not even an AC0 parity circuit. The function actually has an AC0 circuit of depth d and some size s. But even if you want to construct AC0 parity formulas for this function, even if you allowed parity gates now and you want to construct formulas for this function of the same depth, then the size has to be something like s to the d. Okay? So it's a stronger than simply an AC0 parity circuit versus formula separation because f actually has an AC0 circuit. Don't use any parity gates in the circuit. But even if you are allowed parity gates in your formula, you can't do better than the trivial. Make sense? Okay. Right. So in particular, as a corollary, we get that this trivial conversion of AC0 parity circuits to formulas is tight. Okay. All right. So now I'm going to describe some elements of the proof of this result to you. Yeah. And let me start with a brief description of how AC0 parity circuit lower bounds go. Okay. Yes. Sorry, the parity function? Oh, f is not a mod function. F, in fact, has nothing to do with any sort of mod. It's kind of related to the majority function. We'll see in a second. Yeah, we'd like to be able to do this for mod functions maybe. But anyway, so I don't know how to do this for mod functions. Yeah, okay. So, right, so let me start by describing in general how these AC0 parity circuit lower bounds in general go. So again, just like AC0 parity is almost a classical circuit class, right? So soon after AC0 lower bounds were proven, sometime in the early to mid 80s, people started looking at this class. So because it's a very natural thing to consider. And sometime in the mid 80s or 87, I think, Rasburov proved exponential lower bounds for this class. And our results build obviously on his work. So I'm going to describe that work to you a little bit. Okay. So how are we going to argue about AC0 parity circuits, right? So one thing is the little intuition we had about why AC0 circuits are weak. The reason we had was these AND and OR gates are easily fixable to constants by fixing a few inputs. That no longer holds, right? So it's because we have parity gates now, and parity gates you cannot fix. So this is exactly what we used, right? So you have to look at a completely different point of view towards proving lower bounds for these objects, okay? And that's what we're going to do. We're going to take a more algebraic point of view. And what's this algebraic point of view? Well, take any Boolean function you have. It's a function from 0, 1 to the n to 0, 1, and instead think of 0, 1 as the field f2. Okay, so that's it. You think of field 0, 1 as the field f2, and the whole world changes, and range of possibilities open up that you never thought were possible. Yeah. Okay. So what happens, right? So now the advantage is that algebra comes into the picture, and as soon as algebra comes into the picture, you can talk about things like polynomials and other things. Okay, and that's exactly what we're going to do, right? So what we're going to use is some simple facts which are well known in the literature and something that's easy to prove and are useful not just in complexity theory but in vast swaths of combinatorics and other things. Okay, so here are some simple facts. Take any Boolean function, and from now on a Boolean function will take f2 to the n to f2, right? It can be expressed as a polynomial. Okay, it's a polynomial with coefficients coming from the field f2 over the variables x1 to xn. So what do I mean by that? When I say a polynomial expresses a Boolean function, I mean that the polynomial, of course, agrees with the value of the Boolean function at all inputs, right? That's what I mean by saying it expresses. Further, this polynomial has some properties. The polynomial is multilinear. In other words, it does not have any higher powers than 1 of any variable, right? So there's no xi square. And intuitively, I don't need it, right? If xi is only 0 or 1, what's the point of having xi square? I can always replace it by xi, and indeed, I don't need it. So if I have a multilinear polynomial, the monomials in my polynomial are just products of subsets of variables, right? Products of, just subsets of variables. So in particular, the degree of any polynomial can be at most n, right? So we have polynomials of degree at most n that represent my function. And finally, the polynomial is unique, okay? So every Boolean function is represented uniquely by some multilinear polynomial, okay? So none of these facts are hard to prove. In fact, the fourth one is probably the only one that requires a little bit of an argument, but it's something that's very useful in combinatorics. I think it's it's an amazing thing. Okay, so I hope all these things are clear. So what we are going to do is now represent functions as polynomials and look at the complexity of these polynomials in some sense to argue about these functions. Yeah, and in particular we'll be talking about the degrees of these polynomials. So since the degree can be at most n, for us a degree n polynomial is a very high degree polynomial. So that's not something that is easy or simple. Whereas degree is much smaller than n, like a constant or log n is going to be very low degree polynomials, and therefore simple. So functions represented by low degree polynomials are in some sense simple. Okay, so let's just see a few examples. So here are 3 functions we've seen already: the parity function, the AND function, the OR function. So how do we write these as polynomials? Well, it's very simple, right? The parity function is just the sum of the input bits, right? That's what it is, because summing modulo 2, you just sum the input bits. So it's a polynomial of degree 1. So it's a very simple Boolean function now. That's great, right? Because we want the building blocks of our circuits to be simple, and parity is a building block. Simple, that's fantastic. Okay. Now we have the AND function. Here the situation is not so good. So if I want to represent the AND function as a polynomial, obviously I'll just take the product of the variables, right? But unfortunately this has degree n. Okay, so that's not great. Okay. The OR function, how would I represent the OR function as a polynomial? Well, I could always use De Morgan's laws and convert it to the AND function. And if I do that, I get a polynomial that looks something like this. It's not really important that this is the polynomial. What's important is that again it has degree n. So again, not great. Okay. So but this is in general how Boolean functions can be represented as polynomials. And as I said, these polynomials are unique. So it's not like we were stupid in our choice of polynomial and we ended up with a degree n polynomial. Any polynomial we choose would be degree n. So this is not great. Okay. All right, so what we would have liked to say is that if a Boolean function has a small AC0 parity circuit, it can be represented by a simple polynomial or a low degree polynomial. But obviously this is a lost cause because the AND function of course has AC0 parity circuits of small size, but it has degree n. Okay? So the way we salvage the proof here is to kind of give up on representing functions as polynomials exactly, but do so approximately. Okay? So we are going to use this idea, but we're going to give up on representing f exactly as a polynomial, but represented by a polynomial almost everywhere in a way I make precise. Okay? All right. So what do I mean by this? So start with a Boolean function f and some polynomial now, not necessarily representing f. I say that p epsilon approximates f. Okay? Epsilon is some parameter between 0 and 1. So p epsilon approximates f if it agrees with f on all but an epsilon fraction of the inputs. Right? If it agrees with f almost everywhere, then I say that p approximates f. Okay? So we are giving up on exact computation. We are going for approximate computation in the hope that now our complicated looking AND and OR functions suddenly become very simple. Right? Yeah, and this is very easily realizable, right? So the AND function, what is the AND function? Right? The AND function is 0 almost everywhere except for the one point which is the all ones vector where it's 1. Right? So it's a right? So if I just ignored that point, if I kind of assume that it wasn't there, then I could represent it by the 0 polynomial. Right? What that means is that the AND function is 1 over 2 to the n approximated by the 0 polynomial, constant degree polynomial. Right? So if this is my point of view, the AND function suddenly becomes very simple. Of course, the parity function continues to be simple, right? Because it doesn't matter, I don't have to erase any points, the parity function is always a low degree polynomial. The OR function for a similar reason is approximated by the constant 1 polynomial. Okay. So that's the great thing about polynomial approximation. Now suddenly what looked complicated in the exact world looks easy here. Okay. Any questions about okay. All right. So this is what Rasborov proved, right? So we just talked about the building blocks of our circuits, but what about the circuits overall? So Rasborov had this amazing paper in the 80s where he was able to show that not just the AND, OR and the parity functions, but any function that has a small AC0 parity circuit can be approximated by a low degree polynomial. Okay? So if you start with a circuit of size s and depth d, you can approximate it, let's say on 90% of the inputs you get the function right. So you can approximate it to error 1/10 by a polynomial of degree polylog s. Right, so I'm being, unfortunately, I need to be a little precise here in order to state the result. So it's like log s to the d minus 1. Right? But just to get a sense of things, you should think of s as a polynomial. So s is like n squared, and d is some constant like 100. Then this thing is like polylog n. Right? And recall what we think of n as very large, and obviously polylog n is much smaller than n. So this is actually a very simple polynomial. Right? So if I want to represent f exactly, I might need degree up to n, but if I want to represent f only approximately, I only need degree polylog n. Okay? So this is a nice polynomial approximation lemma due to Rasborov, and this is going to show up later in our proof as well. So any questions about this lemma? Yeah. So 1 by 10 can be, yeah, so that's a good question. So 1 by 10 can be any delta here, but then we'd have to pay a log 1 over delta multiplicatively in the degree. Yeah, so I'm going to come to that. That's a good question. Yeah, anything else? Okay, all right, so this is a polynomial approximation lemma. Okay, so using this, Rasborov was actually able to prove a lower bound for a nice explicit function. And which function was it? It was the majority function. Okay, so that's again a function that's easily stated. So you have the majority of n bits, which is 1 if there are more than half the bits are 1, and 0 if more than half the bits are 0. Okay, that's the majority function. Okay. So again, this should not look like any of the AND, or parity functions, right? Yeah. Intuitively, they have some sort of algebraic structure now, whereas the majority function lacks that algebraic structure. And what Rasborov showed was that any polynomial that even approximates this majority function must have large degree. Okay? It's not just if you want to represent this function exactly, even if you want to approximate it, let's say on 75% of the inputs, the any such polynomial that does this must have degree square root n. Okay. All right. So what do we have? We have two things. Any function with a small AC0 parity circuits has low degree approximations. Any approximation for the majority function must have large degree. Putting things together, no small circuit can compute the majority function. Okay. So this is the polynomial approximation lemma. This is the majority approximation lemma. Putting things together, you get a lower bound for AC0 parity circuits. Okay. So again, I'm going to be a little bit pedantic and write down what kind of lower bound we get here. That's majority. Okay. It's a little bit worse than what we get for parity. So here we get 2 to the n to the, here we get 2 to the square root n, here we get 2 to the n to the 1/4, here we get 2 to the n to the 1/6, 2 to the n to the 1/8, etc. Okay, so they're off by a factor of half in the double exponent. It's not known whether this is tight, unfortunately. Okay. All right. So yeah, so what we saw for the parity function was that the lower bound from Hofstad's theorem, the first column here, is actually tight. Fortunately, for the majority function, we don't know that this is tight. Okay, and this is going to show up. It's going to be a bottleneck later on in our theorem. Okay, so majority, the best circuits we know roughly have this size, the same size that we had for the parity function. But the best lower bounds we know are roughly of this size. Okay, so there's a kind of a big gap between the two. So these are AC0 circuits. We don't know anything better for AC0 parity circuits. Yeah, we don't know how to use parity gates to compute majority. Okay, right. I should have actually written AC0 parity here. All right. Okay. So yeah, it's very unfortunate. And recall that the fact that our Hofstad's lower bound was tight was important in the AC0 formula versus circuits thing, because all we did was prove an improved formula lower bound, and we already had a circuit upper bound from the fact that Hofstad is tight, and then we could do stuff. Right? And here we don't have that result. So now our task gets a little harder. Okay. Yeah, so for example, in the case d equals 3, the lower bound we have is 2 to the n to the 1/4, but the upper bound is like 2 to the, not even 2 to the square root n, it's slightly worse, 2 to the square root n log n. Yeah, so it's a problem. Okay. All right, so now let me tell you a little bit about our proof. Okay, so how do we get around these bottlenecks, and what do we do in order to prove the formula versus circuit separation for AC0 parity? Okay, so here's what we prove. First of all, we prove an improvement over Rasborov's polynomial approximation lemmas, assuming that the circuit is actually, well, it's a formula, assuming that it's a formula that we're dealing with. Okay, so what's the stronger approximation lemma? So previously we had some degree. It was log s to the d minus 1. So let me write it down carefully. So previously Rasborov tells us that AC0 parity circuits of size s and depth d have approximating polynomials of this degree, log s to the d minus 1. This is for circuits. And this is formulas. Okay. Right? And so it might look like a funny improvement, but really the way you should think of this is as log s to the 1 over d to the d minus 1. Okay. So it means that to get the same degree for circuits that you get for formulas, the formulas would have to be, the size of the formula would have to be s to the d here, right? Because the inverse function, to get the same thing here, you'd actually have to substitute x to the d here to get that. Okay, so that means that there's some sort of equivalence between circuits of size s and formulas of size s to the d. Okay, and this is where the blow up is coming from. All right, good. Okay, that's the stronger approximation lemma. Okay, so we can already use this from this majority approximation lemma of Rasborov. We can put that together with the stronger approximation lemma to say that any AC0 parity formula for the majority function has an improved lower bound than what we get for circuits. So for circuits, we just get what's in the exponent without the d, but now we get an additional d in the exponent. Okay, It's the same thing. Just say, okay, anything that is that has a small formula has a low degree approximating polynomial. The majority function does not have a low degree approximating polynomial. Put those two things together and you get this. Okay. So it's the same thing. So you just work it out, and the parameters are exactly what you got for circuits, but now raised to the power d. All right. So it looks, once you have this, it looks like all the things are in place. You're ready for your circuits versus formula separation. But unfortunately, the problem is we don't have circuits of size 2 to the n to the 1 over 2 times d minus 1 for the majority function. Okay, so we don't really, the lower bound that we got for the majority function is not tight. Okay, so that means we don't yet have this formula versus circuit separation at this point. So we need to work just a little bit harder. Okay, so what do? Well, we change our function. It's not the majority function anymore, but we look at slight variants of the majority function. Okay, the variants are approximate majority functions. Okay, so what's an approximate majority function? There are many such in the literature. The one we look at, an approximate majority function is just a function that agrees with the majority function almost everywhere. Think of delta as like, again, like, I don't know, 1 over 10 or something, so it agrees with the majority function on 90% of the inputs. Okay, so notice that this is not one function but a class of functions. Any function that agrees with the majority function on 90% of the inputs is an approximate majority. Okay, right? So it turns out that from the point of view of our lower bound, it doesn't really matter whether you're dealing with the majority function or an approximate majority function. You get the same lower bound. Okay? In this entire Rasberov framework, we don't really use the fact that the circuit is computing majority exactly. We only use the fact that the circuit is kind of approximating the majority function. Well, what do I mean by that? Assume that you have an approximate majority like this, which is actually computed by a small AC0 parity circuit, right? Using the polynomial approximation lemma, since f has a small circuit, you could approximate it by a low degree polynomial, right? But on the other hand, f is an approximate majority, so f is pretty close to some majority function, to the majority function, right? So putting these two things together, what you see is that majority is approximated by a low degree polynomial, right? And from the majority approximation lemma of Rasberov, we know that this is not possible. Okay? So the same proof technique, it actually just goes through as is and shows that f has no low degree, f cannot be computed by a small AC0 parity circuit. All right? And indeed, even in our machinery, if we use a stronger polynomial approximation lemma than the one that Rasberov gets for formulas, what we get is that any AC0 parity formula, even for an approximate majority, must have size 2 to the d n to the 1 over 2 times d minus 1. Okay, the same lower bound we get for majority, but we now get it for any approximate majority. And we don't have to do anything. Okay, it's just built into the proof technique. Okay, is that clear? All right, good. Okay, finally, what we do in order to complete the cycle and show the separation between circuits and formulas is that we show that there is an approximate majority that has an AC0 circuit of the required size. Okay, so in this upper bound, we don't even need the fact that we have parity gates. We just come up with an AC0 circuit of depth d and so and so size that computes some approximate majority. Okay, so this is a kind of an ugly part of the paper, and I'm not going to say much about this. But for those of you who know, this is kind of based on a famous probabilistic construction of circuits by Valiant back in the 1980s. So back in the 1980s, so Valiant constructed these probabilistic formulas of large depth, so they have depth log n, that compute the majority function exactly. Okay, they compute the majority function exactly. It's a very beautiful construction. Okay, and sometime in the around 2009 or so, this result was improved by Kazuyuki Amano, where he showed how to scale this result down to constant depth, and now it's for just computing an approximate majority. Okay, so Kazuyuki Amano looked at exactly this. He wanted to compute an approximate majority, but he wanted to do it in constant depth. And now how good can you do? So the only thing about Amano's construction was that it constructed formulas, probabilistic formulas, not probabilistic circuits, probabilistic formulas. And we've already seen on the last slide that you cannot get probabilistic formulas of this good a size for approximate majorities. Right? So all we have to do is kind of modify Amano's construction to use the fact that we are constructing circuits and not formulas. And then we are actually able to get a better upper bound. Okay? And this upper bound, the ideas behind this were independently, were discovered well before us by Huri, Mcgann, and Petoskey, who constructed better probabilistic circuits for computing the majority function again exactly. Okay, so they had already improved on Valiant a little bit, and we used the same ideas to improve on Amano. to get a smaller circuit. Okay.
So separating f is not known.
Yeah, so a separating f is not explicit. Okay. A probabilistic circuit is a circuit that's constructed with probability. So we just argue that the circuit exists without giving an explicit construction of the circuit. So we don't tell you actually where the function f agrees with the majority function and where it doesn't. We just pick a random circuit and show that it agrees with the majority function almost everywhere, and then we fix the randomness, and so a circuit will be for some particular fixing of the random bits. The function need not be explicit. So in these contexts, right, so in the context of separating circuits from formulas, even a non-explicit separation is interesting because counting arguments no longer go through. So it's a great question to make this explicit, but even non-explicit is interesting.
So counting arguments don't go through, meaning the number of functions which approximate majority is small?
No, counting arguments don't go through in the sense that the number of functions that have circuits of size s is much smaller than the number of functions that have formulas of size s to the d or so. So you cannot just say that there exists one by counting. Yeah. Yeah. Any other questions? Right. Yeah, we give a family of circuits, but right. Yeah, we give a family of circuits. No, so most of them actually compute majority. Not exactly. Most of them agree with the majority function almost everywhere. In fact, on every input, most of them compute the majority function correctly. So in particular, one of them computes the majority function correctly almost everywhere. It's a probability distribution. It does not compute the majority function exactly. Right. In fact, they cannot actually. So it's known that if you want to compute the majority function exactly and you don't have parity gates, then this is the right lower bound. Yeah. Any other questions? Okay, great. So that's it. So this is, I guess, an approximate majority construction. This probabilistic, not explicit. Then we have the stronger polynomial approximation lemma, and you put these two together and you get the main theorem. Okay, so that's more or less an outline of the proof. Which time do I have? Much time do I have? Should have like 20 minutes. Wow. Okay, that's fantastic. Are you sure there are no more questions? Okay. All right. Okay, so I thought now I'd kind of just describe a little bit about how the proof of the stronger approximation lemma works. Okay. So again, this is very it closely follows Rasborov's proof of constructing approximation lemma, approximating polynomials for circuits. Only we need to optimize it a little bit to use the fact that we are actually working with formulas. Okay, so let me describe it to you. So this is the lemma again. So you have an AC0 parity formula now. So it's important that it's a formula of sizes and depth d. There are polynomials of degree log s over d to the d minus 1 that approximate f on 90% of the inputs. Okay, so that's the lemma. So though this lemma is nicely stated in this way, this is not the best way to prove it. Okay, the reason is that approximating polynomials are kind of cumbersome to deal with. So if you have two approximating polynomial for a function f and an approximating polynomial for a function g, if you compose them together, you can't compose just the approximating polynomials and get a new approximating polynomial. Okay, so approximating polynomial is kind of ugly in that sense. So we modify the notion a little bit, yeah, and that will help us do the construction. Okay, so what is this modified notion? This is called a probabilistic polynomial. Okay, so what's a probabilistic polynomial? It's very simple. So if you think of a polynomial as a simple algorithm for your Boolean function, a probabilistic polynomial is a randomized algorithm in that moment. Okay, so a polynomial is an algorithm. It's always outputs the same answer, obviously, on any given input. A probabilistic polynomial is a randomized algorithm. So what does that mean? A probabilistic polynomial is just a random polynomial from the space of polynomials. Okay, so what's a randomized algorithm? One way of viewing a randomized algorithm is that you toss all your coins beforehand, and fixing the coin tosses, you run a deterministic algorithm. Similar to that, a probabilistic polynomial is you have some coins, you toss it, pick a polynomial, and then run that polynomial on your input, and that's a probabilistic polynomial. Okay, it doesn't matter how you use your coins to pick your polynomial. It could be any old ugly way. I mean, anything that you want. You just use your randomness, pick a polynomial some way, and then run it on your input. That's a probabilistic polynomial. Okay, so I'm going to use this funny p to denote probabilistic polynomials, hopefully consistently. So a probabilistic polynomial is said to have degree d if the random polynomial that you pick always has degree at most d. Okay, so you're using your randomness, but only to pick, say, quadratic polynomials. Then it's a probabilistic polynomial of degree 2. So, right, so this is a randomized algorithm, and of course when does a randomized algorithm succeed? Well, your polynomial, let's say, computes a Boolean function, let's say delta computes a Boolean function if on every input you compute the function correctly with probability 1 minus delta. Okay, on every input. So this is the difference between the notion of approximation we saw earlier and the probabilistic polynomial here. There we just needed to get the function right on most inputs. Yeah, so the randomness was over the choice of the input. But here the input is worst case, which is standard in randomized algorithms, right? The input is worst case, but the probability is over the choice of the random coins of the algorithm. And over the choice of these coins, the probability that the polynomial makes an error is at most delta. Okay, so that's a probabilistic polynomial. Okay, yeah, it's exactly, you should really think of it exactly as a randomized algorithm. All right, so a couple of examples. So here's a cheating example. Any deterministic algorithm is a randomized algorithm. So any polynomial is a probabilistic polynomial. It's just that I don't use any randomness. Okay, so that's perfectly legal. So that's a probabilistic polynomial. What's a slightly more non-trivial example? So here's one. It's in fact the only example, I think. It's a universal example. We don't use anything else, I think, in real life. So, so let's say you have 4 input bits, y1, y2, y3, y4, that you pick independently and uniformly at random. So 4 of them. Okay. And here's my probabilistic polynomial. Now I'm going to use these random bits to define my polynomial. So my polynomial is on 2 bits, x1 and x2, and here's the polynomial. Okay, so it's 1 plus x1 times the first random bit plus 1 plus x2 times the second random bit plus 1 times a similar thing with y3 and y4. Okay. So it's nothing very simple, very complicated. It's a product of 2 linear functions, but note that the linear functions are random, right? Because y1 and y2 are random bits, so the linear functions are random. So they're not like fixed linear functions, so it's a distribution over polynomials. Okay, right? And the reason this particular polynomial is interesting is that it actually computes the AND function with good probability. Okay, so it computes the AND function with error at most 1 over 4. Okay, so this is a probabilistic polynomial that 1/4 computes the AND function on 2 bits. Okay, it's not very hard to argue since I have lots and lots of time. Let me just go through it. Right, so assume that. So what kind of inputs does the AND function have? Right, there are 2. There's one where all the bits are 1, and there's ones where there's some bit that's 0. So let's look at the case when all the bits are 1. Right, so let's say x1 is 1 and x2 is 1. Well, if x1 is 1, the coefficient of y1 is 0, so that term disappears. Similarly, the coefficient of y2 is 0, so that term disappears. So the first linear function is just 1. And for the same reason, the second linear function is 1, so I always output 1. Okay? So if x1 and x2 are both 1, this probabilistic polynomial actually is not very probabilistic, it just always outputs the right answer. Okay, that's great. Okay? If x1 and x2 are not both 1, so just for as a representative case, let's look at the case when both of them are 0. Let's say x1 and x2 are both 0. Then what you get is y1 plus y2 plus 1, the first term, right? So y1 is a random bit, y2 is a random bit, y1 plus y2 you can check is a random bit. Okay, so y1 plus y2 plus 1 is just the negation of y1 plus y2, that's again a random bit. So the first term is a random bit and the second term is a random bit, and the probability that this thing does not output 0, right? The 0 is what we'd like to output. The probability that this thing doesn't output 0 is the probability that both the random bits are 1, which is 1/4. Okay, so and the same thing works when one of x1 or x2 is 0. Okay, so on every input, right? So again, the probability is not over the input, and every input we compute the right value with probability at least 3/4. So this is this 1/4 computes the AND function. Okay, great. All right, so that's examples of probabilistic polynomials. Okay, so here's a few facts about these polynomials that we're going to use in the proof. Okay, and all of these are very elementary and simple to prove. Okay, the first thing is that these are intimately related to the notions of polynomial approximation we saw some time ago. In fact, they strengthen them. Okay, so if you have a probabilistic polynomial, so this is that funny piece. So it's a probabilistic polynomial of degree d that delta computes f. Then by averaging, you can get a deterministic algorithm, a deterministic polynomial, not probabilistic polynomial of the same degree, that now delta approximates f. Right? And the reason is just averaging. If you have a random polynomial, if you have a distribution of polynomials such that on every input, a random polynomial with respect to a distribution gets the function right with high probability, that means most of the polynomials in your distribution are right on each input, then there's one polynomial in your distribution that's right on most inputs. Right? And therefore, from a probabilistic polynomial, you could always determinize, but now you will be erring on a delta fraction of inputs, but okay, that's something you have to pay. So you can always do this, right? So when we construct our probabilistic polynomials, they always immediately imply approximating polynomials by this thing. So we'll stick to probabilistic polynomials. So and now let's consider the building blocks of our circuits, right? So the parity function actually has an probabilistic polynomial of degree 1. Why? Because the parity function is a degree 1 polynomial. It's a deterministic polynomial of degree 1. Every deterministic algorithm is of course a randomized algorithm, so the parity function has a probabilistic polynomial of degree 1. Right? So the non-trivial thing is to do this for the AND and the OR functions. Okay? And this is what Rasburov did. And this is just a simple reworking of the second example we saw on the last slide. Okay? So let's take the AND function on n bits. The AND function on n bits has a probabilistic polynomial of degree log 1 over delta that computes it with probability 1 minus delta. Okay? Right? So to understand why this statement is really interesting, note that there is no dependence on n in the degree. Right? I mean, the number of bits could be anything. It could be a zillion, and you want to get it right with probability 90%, you only need to pay a constant degree. Okay? So it's an amazing result. Okay? And now again, by applying De Morgan laws, you could always convert an OR function to an AND function, apply the same trick, and you can get the same result for OR. All right. So putting these together, what we have are probabilistic polynomials for all the building blocks, the individual gates of our circuits / formulas. And using this, we can prove the result. Okay? I'll just need one last thing, and which is just very natural for any sort of randomized algorithm. Right? Whenever you have a randomized algorithm, you think about error reduction. So if I look at probabilistic polynomials of degree d that, let's say, compute my function correctly with 90%, with probability 0.9 on every input, I could ask, what if I want to reduce this error further? Right? And this is related to what Nutan was asking some time ago. So if I want to reduce my error from 0.1 to some small number delta, then I can always do this by paying a log 1 over delta, a multiplicative log 1 over delta in my degree. Okay? And how would I do this? Well, it's exactly what you would do for algorithms. Right? So if you have a randomized algorithm and you want to reduce error, what do? You run it a bunch of times independently and take the majority vote. And that works here. So you just take t independent and random copies of your probabilistic polynomial p. So I'm calling them p1 to pt here. And t will be roughly like log 1 over delta. That's how many times you need to repeat your algorithm to get the error down to delta. And then take the majority vote. Okay? And that's your final probabilistic polynomial. Okay? It's clear that this is right with probability 1 minus delta on every input, because each one is right or wrong only with probability 0.1. And the majority function, being some Boolean function on t bits, can be represented as a polynomial of degree t. Okay? So the outer thing is a polynomial of degree t, the inner things are polynomials of degree d, so the overall degree is d times t, which is d log 1 over delta. Okay? So that's it. Yes?
Approximately compute majority, you can get a lower degree polynomial.
I could, what do you mean? I could get a low?
Only interested in approximately computing.
Oh, good one. Oh, all right, really good. Yeah, okay. So if I approximately compute this, I could reduce my degree further, but it turns out not to help in this context. Yeah, it turns out not to help in this context. Yeah. So, yeah, if I use the fact that, okay, so if I use the fact that I'm only approximately computing majority, it turns out I have to blow up this log 1 over delta or something larger, and then the gains from this are offset by the losses from that, and then it turns out. But that's a great, yeah, it's a great idea. Yeah. Okay. All right, so, okay, so now I'm ready to prove the stronger approximation lemma. And now I've stated it in the language of probabilistic polynomials instead. So we're not going to construct a polynomial approximation directly, we'll go for a probabilistic polynomial. And how are we going to do this? Well, we're going to do this, so I'm not going to describe the general thing, I'll describe it in a special case. So my formula will be kind of structured. So I look at formulas of size s, but moreover have the property that every gate has fan-in exactly t. Okay? So pick t to be some parameter. Every gate in the formula has exactly t inputs feeding into it. Internal gate, of course. Right? So let me call such a formula a t regular formula. Okay? So regular formulas is something that have been investigated in arithmetic circuits by Neeraj, Ramprasad, and others. So this is just a simple variant that's easy to describe. The proof actually works in more generality, and I'll say a couple of things about that. Okay? So let's look at a formula like this. Every internal gate has exactly t inputs. And so the size of this formula is clearly t to the d, right? T, you just multiply d times, so size is t to the d. So what we should aim for here looking at this expression up here, is that we should aim for a probabilistic polynomial of degree log t to the d minus 1. Okay, right? Because if our stronger polynomial approximation is to be true, here we should get log t to the d minus 1. Okay, and we're going to prove this by induction on the depth. All right. So that's it. So that's the strong approximation lemma. So let's do it. So induction on d. The case d equals 1 is very simple. The case d equals 1 is when you have a single gate. Those are building blocks of your circuit. And there we have probabilistic polynomials of constant degree by this Rasborov's construction and the fact that parity gates are already polynomials of degree 1. Okay, there's nothing to do there. So base case is simple. It's all in the induction. So what about the induction? Well, the induction, the case, the formula looks like this. So you have some gate which computes a function g, and into it are feeding the outputs of these sub formulas f1 through ft, right? Exactly t of them. And each of them in turn have probabilistic polynomials already of the correct degree, right? So by the induction hypothesis, we have these probabilistic polynomials pi that compute each fi correctly with high probability, probability 0.9, and the degree here is log t to the d minus 1. Okay. So now what we do is we take the building block. So the first thing we do is we reduce the errors of these polynomials. Okay. So since we are going to put them together, we want none of them to make a mistake, because one of them makes a mistake, we might screw up. Okay, so none of them should make a mistake. So we reduce the error to something like 1 over t. Okay, so to be precise, something like 1 over 20 t or whatever, it doesn't matter. So we reduce the error to something like 1 over t. So since the error is so small, with high probability, none of them is going to make a mistake. Okay, and how much do we need to pay in order to reduce the error? Well, it's exactly the error reduction that we saw a few slides ago. We'll have to pay log 1 over the error. So it's like log t. So the degree goes up from log t to the d minus 1 to log t to the d. Okay, so that's a little bit, right? So that's what we have now, log t to the d. And now the output gate has a probabilistic polynomial of constant degree. Again, this is Rasborov. Compose, and you're done. Okay, so it's really simple. Okay, so why does this differ from the circuit thing, right? So if you've seen the standard circuit thing, what you do is that you just construct probabilistic polynomials of very small degree for all the gates and just compose them. Okay, and what you do is intuitively you take a union bound over all the gates in the circuit at one go, right? Here you're just using the fact that each gate only depends on a few inputs. So you're not taking a union bound over everything, you're only reducing the error to 1 over t, where t is the fan-in of the circuit, not to 1 over s, where s is the size of the circuit. Okay, and that's the gain essentially, and that's what makes formulas different from circuits. In circuits, every gate on a subsequent layer can depend on all the gates of the previous layer, so you have no choice but to do a union bound over everything, whereas here it's more restricted, so you look at that and then that's what you get.
So
Yeah.
there is this order 1 degree that we keep multiplying at every step.
Right, so it's order log t whole to the d minus 1. So there's a constant times log t whole to the d minus 1. In fact, it's actually uglier. It's order of order log t whole to the d minus 1, but I didn't want to write that. Yeah, because at d equals 1, you don't get 1, you get a constant, but it doesn't matter. Okay. All right. All right, so that's more or less it. Yeah, so that's the regular case. What about the irregular case? Well, it's similar, it's just a little more computationally intensive. So in the general case, what you have is you don't have these guys all have the same fan-in. You do have t formulas, but they could have different sizes. Okay. So again, by the induction hypothesis, you have pi that computes fi. And now the PIs all have different degrees, right? So if you have a large formula, you might have large degree. If you have a small formula, you have small degree, etc. Okay? So now what you're going to do is, now you're going to reduce the errors of these guys, but the error for each formula fi will be different. Okay? For example, if f1 is a big formula, you already paid a lot in degree, so don't reduce error all that much. But if f2 is a small formula, you paid very less in degree, so you can afford to reduce the error by a lot, and you keep doing this. So your pi primes now, which are the error reduced polynomials, are defined with respect to error that kind of proportional to the size of the circuit. So the smaller the size of that sub formula, the smaller the error, so the more you can, because you can afford to pay more in the degree. So the degree now blows up roughly by log s over si. Okay, well si is the size of the ith formula, right? And again, now you do the same thing for the output gate. You just use Rasborov and compose, and you analyze things in a kind of the simplest possible way. You say the degree of this is at most the degree of this times the max of the degree of the inner guys. Okay, and now if you kind of analyze this carefully and look at the recursion, etc., it all works out and you get the right answer. Okay, that's not something I'm going to do, but it's quite, it's a nice thing to work out. So that's it, I'm done. Oh, right on time, fantastic. So so just a couple of questions before I conclude. So one thing in all this is that we kind of completely sidestepped a bottleneck in the proof, which is what is an optimal AC0 circuit for majority. Okay. So I think that this is a really fundamental question that strangely enough doesn't have a tight answer. Even for d equals 3, we don't know the right answer. It's a great question. So there the lower bound is 2 to the square root n, the upper bound is 2 to the square root of n log n, and we don't know what the right answer is. So that's a fantastic question. And as Meena and a bunch of others pointed out, our approximate majorities, our lower bound candidates, actually probabilistic constructions. While this is non-trivial, we would always like an explicit construction. And so can you find explicit majorities, approximate majorities that have small AC0 circuits so that our lower bound becomes completely explicit? Yeah, that's all I have. Thanks. Yeah, same thing goes for AC0 with any mod p for p constant. Yeah, absolutely. As soon as we add two mods, yeah, there are simpler questions that are harder. So yeah, stop.
So one could presumably ask the same question for PC0 formulas and circuits.
Absolutely, yeah, absolutely.
But I have not heard of anything in that regard.
Right, again, that's probably because, oh, yeah, so you could ask. We have some lower bounds for TC0 circuits, but they're very weak lower bounds. They're kind of sublinear lower bounds. Right? You could ask if they can be proved. Yeah, I don't know. Yeah, it's a good question. I'm not sure. But even there, we don't, yeah. The lower bounds that we do have, we don't know if they're tight, so you'd have to change the question a little bit. Yeah, yeah, maybe.
Well, we have some tight lower bounds for depth to unweighted majority.
Depth to unweighted majority, yeah. So for example, for the parity function, we have right. We have some lower bounds, but they're not known to be tight. Yeah. Again, it's very you'll be very careful. You're talking about gates. You're talking about wires. For approximate parity, we have the right answer in terms of both gates and wires. But there, at depth 2, how much difference can you tell? So you'll have to go to large D, and then yeah, I'm not sure.
We don't have lower bounds.
We have very weak lower bounds. We have lower bounds that are like n to the 1 over 2 times d minus 1 for approximating the parity function, and that's tight. But now you can ask, okay, circuits versus formulas, can you see a difference? I don't think you should be. Well, maybe you can. I don't know. Yeah, maybe you can. But they're very weak bounds. Yeah.
Somehow here you, I mean, the explicit is not the thing you care most about.
That's right.
Is it clear that we must first put lower bounds for circuit class to answer this question?
Oh, it's a good one. Oh, so the question is that we don't care about explicitness. So maybe we can always come up with non-explicit lower bounds without doing the explicit thing. Well, at least you would prove, and I think end up proving non-trivial lower bounds, because at least you would have, instead of picking a random function, you're picking maybe a function from some smaller class. So now you could make that randomness part of the input and maybe use that and give a non-trivial lower bound as well. So it may be that this will end up proving some sort of, so I'm not sure about that though. Oh, it's great. So in the arithmetic world, the problem is that we don't have constant depth circuit lower bounds. Right? So all this is applicable when you can prove something about constant depth circuits or formulas, and then you can ask, is there a separation between circuits and formulas? In the arithmetic world, at least over, yeah, let's say large, let's say depth 100, I don't know of reasonable ways of proving lower bounds, but maybe I'm wrong. Yeah, something, yeah, I don't know. When the field size becomes big, of course, very difficult. When the field size is small, of course, this already does it over F2, but now you could ask over F3, and then all sorts of mod 6 questions come into play. I'm not sure, so it's some weird